Lecture 27 covers sections 8.4 and 8.5. At the end of today's lecture, you should be able to formulate the time constants for RL and RC circuits when sequential switching occurs. You should also be able to analyze the stability of RL and RC circuits when switching occurs. For us to begin, sequential switching is when two or more switches within our circuit change state at different times. To analyze the behavior of this type of circuit, we need to use the same method we developed for RL and RC circuits, but we have to keep a time history of the behavior, i.e. we have to know how our voltage evolves as a function of time or our current evolves as a function of time. Our textbook provides no explanation of how to solve these problems, so this will be the only source of information. To begin, let's look at example 1, where we're given the following circuit. At time t is equal to 0, switch 1 is opened. Then 35 milliseconds later, switch 2 is opened. If we want to determine our current as a function of time within the period of 0 to 35 milliseconds, and thereafter, we need to employ the behavior of an RL circuit with sequential switching. To begin, let's look at our circuit. We have a 60 volt source that's applying a potential to a 4 ohm resistor. This 4 ohm resistor is connected to a 12 ohm resistor, as well as a 3 and 6 ohm resistor, and downstream an inductor, as well as an 18 ohm resistor. Our inductor has an inductance of 150 millihenries. We note that when both switches are closed, our inductor is going to act as a short circuit. That is, since there is no time rate of change of current going through our inductor, there is no voltage potential established across, and thus our 18 ohm resistor is neglected from our circuit. Thus, our circuit will look as follows. From time t is equal to minus infinity to 0, switch 1 is closed, and then from time t is equal to minus infinity to 35 milliseconds, switch 2 is closed. Since our inductor is acting as a short circuit, our 18 ohm resistor is bypassed. Now, to determine the behavior of I of L of t, we need to apply KCL at node A. In doing such, we can determine the current going through our inductor, i.e. our short, from negative infinity to 0. Thus, we have I1 exiting our voltage source, I2 running down our 12 ohm resistor, I3 running down our 6 ohm resistor, and IL running through our 3 ohm resistor down our short. No current will run through our 18 ohm resistor. If we employ Ohm's law to our KCL equation in terms of our node voltage at A and ground, we can say I1 is equal to 60 minus VA per 4 ohms, and this is equal to I2, which is VA per 12 ohms, plus I3, which is VA per 6 ohms, plus IL, which is VA per 3 ohms. We can solve this equation, and we find VA is equal to 18 volts, which implies IL from our time period, negative infinity up to 0, coming from the negative side, is equal to 6 amps. This will be our initial current within our system. Now, for a time period of 0 to 35 milliseconds, switch 1 has opened. Switch 2 is still closed. Thus, our 60 volt source is applying a potential around our loop that contains our 4 and 12 ohm resistor. Since ground is defined as our bottom node, our voltage source is no longer supplying the right-hand side of our circuit. We recognize that our 3 and 6 ohm resistor exist in a series configuration, which gives us a 9 ohm resistor, which is in parallel with our 18 ohm resistor. Thus, our inductor, which was originally carrying 6 amps, is now supplying an equivalent resistor of 6 ohms. Our time constant within this period of 0 to 35 milliseconds is our inductance per our resistance of our circuit, or 150 millihenries per 6 ohms, or 25 milliseconds. Now, the current is a function of time. I of t is equal to I sub sc plus I naught minus I sub sc, this quantity times e minus t per tau. We know I sub sc is equal to 0, for we have no source current. Therefore, I of t is equal to initial current, I of naught, which was 6, times e to minus t per tau. This means our current is equal to 6 e to minus 40 t. In the time period, t is greater than 35 milliseconds, switch to open. In this particular situation, all we now have is our current, I sub L, running through a loop that contains our 3 and 6 ohm resistor. Now, the current running through our inductor when time is equal to 35 milliseconds is simply found by taking our expression for I of t from our previous time interval and inserting t is equal to 35 milliseconds. Thus, I of t at time t is equal to 35 milliseconds is 1.48 amps. Now, to determine the current After 35 milliseconds, we need to solve our expression for our time constant. Tau is equal to L per R, where our current is now running through a loop where our equivalent resistance is 9 ohms. So our time constant is now 16.6 milliseconds. Thus, our new expression for current, I of t, is equal to our initial current, 1.48 amps, times e to minus t per our time, 0.035 seconds, per our time constant, tau. Or I of t is 1.48 e to minus 60 times the quantity t minus 0.035. We note that our time has to take into account where we depart, i.e. 0.035 seconds. That is, when time t is equal to 0.35 seconds, we have e to the 0, this term drops out, and we're left with our initial current, 1.48 amps.